Hi, this is an example problem on relativistic velocity addition from chapter 28. Pause for a moment to read the question. So in this case, we're told that we have two spaceships. They're both traveling as observed by someone at rest on Earth at 0.75 c speed, but they're going in opposite directions. So the first thing that's super important when we're doing relativistic velocity addition is that we need to go ahead and pick a direction as the positive axis and put the appropriate signs, right? So this one's positive, but this one here is negative. Now, the other thing that we want to remember is the subscripting for relative velocity. This is the same as we did before when we did this in chapter 3 with Galileo. Now we're going to use the updated equation for adding relativistic velocities that Newton gave us, but the idea is similar to what we did before. So for example, looking at the notes here, if I want to know, say we have three objects, right? Each one of these is in itself its own reference frame, and if you are in one of those frames, you believe you're at rest while the other objects are moving with respect to you. In this case, we can relate the velocities, right? So for example, VAE here, a general way to write the equation is to go ahead and write it as a sum of two velocities. You put the A and the E on the outsides, and then the one subscript for the coordinate system you haven't used goes in the middle. Now this is Galileo's formula, but it's the numerator of Newton's as well. The same work applies. Now if we want to reverse any of these subscripts, like the velocity of Earth as seen by spaceship B, well, if we reverse the subscripts, we just get a minus sign, because for the Earth observer, the spaceship's going the same speed but in the opposite direction. Now let's flip ahead to Einstein's formula, which is correct for any speed. It's the Galileo formula in the top with the denominator that looks like this. But the same idea as before, right? If I want the velocity of A spaceship as viewed by the Earth, I can write it as a sum of two V's, AE, they go at the ends, B in the middle. And in the term on the bottom, it's a product of two V's, but again, it's AE at the end, B's in the middle. If I ever want to switch the subscripts, if I need to do that, again, switch the subscripts, put a minus sign. Same idea as before. All right, so we're going to go ahead and label this guy as the Earth here. So that's the third coordinate system, the third reference frame. We've also got the reference frames A and B of the two rocket ships. We're asked, what is the relative velocity between the spaceships in their own reference frames, right? So for example, I'd like to know, what is the velocity of spaceship B as observed by spaceship A? That's what the subscripts mean. Well, I don't have the equation like that over here, right? But I know what to do. I'm going to just follow the same pattern here. So this is going to be V plus V, and I'm going to put a B and an A on the outsides, and on the inside goes the one that we haven't used yet. What's that? That's Earth. And then the denominator, we do the same thing again. It's going to be 1 plus, it's the product now of these two V's, same order of subscripts, divided by c squared. Now let's look what we have. We have AE and we have BE. So it looks like we're good here, BE. But this is opposite, right? This one we got to switch. And we also got to switch it here. So we're going to use the rule again now so that we know that VEA equals minus VAE. And therefore we can go ahead and rewrite this finally. We're going to go VBE minus VAE. I just flipped the subscripts, put a minus sign there. Same thing on the bottom. I'm going to factor out the minus sign here because remember VBE, this didn't change, but I flipped this one to AE, hence the minus sign there, and divide it by c squared still. So again, follow the pattern, use the flipping subscripts with minus signs, and you can always come up with the formula that you want. At this point, we need to go ahead and just plug in the numbers that we have. So VBE, 0.75, multiplied by C. VAE, that's a negative 0.75 times C, all divided by 1 minus, now the product of these two, that's going to be VBE 0.75 C multiplied by VAE, that's a negative 0.75 C, all divided by C squared. And notice in the top, this is what Galileo's result would give you. A negative negative becomes a positive. It's going to say 1.5 times the speed of light. So Galileo would say that the ship A is viewing the speed of B to be plus 1.5 C. Of course, that's not right. Nothing can exceed the speed of light. Here's where Einstein's correction comes in to make things always less than the speed of light. So 1 minus, we multiply the 0.75 times the negative 0.75, and we're going to come up with a value of negative 0.5625 C squared divided by C squared. The C squareds cancel. And that's going to give us 1.5 C divided by 1, and we add the two negatives, right, 0.5625. And doing that last division gives us a value of 0.96 C. Again, less than the speed of light, which makes sense. Now to do the other ship, what is the velocity that ship A is observed to have when viewed by ship B? In this case, ship B assumes it's at rest and sees A moving in the negative x direction. What's that velocity going to be? Well, we can go through the whole thing again, or let's do the simple technique here. Just flip the subscript, put a minus sign, and so this is going to be negative 0.96 C. So again, they both see the other ship at the same speed and in opposite directions. So that's how we can use the relativistic velocity addition formula.